Hello students, in our today's class we shall discuss the percentage calculation of the elements, along with that empirical formula, molecular formula calculations using some examples. If you don't watch the previous video of the mole concept, please do watch that video, as the mole concept is very helpful in solving the questions regarding the both molecular formula and empirical formula. Let us see the questions now and along with the concept. So the first one is percentage of element. So percentage of element means if you take any particular molecule, the molecule is composed of the atoms. If you take the carbon dioxide, it is composed of the carbon and oxygen. Carbon carries a certain type of the mass, oxygen carries another type of the mass. When these two combine and form a new compound, so the mass of the compound will be different from the mass of the both of these atoms. In such cases, how much the mass of every element and its percentage is present in that compound is called the percentage of the element in a compound. So percentage of the element is nothing but the ratio of the mass of the element to the molecular mass of the element multiplied by the 100 is called the percentage of the element. Let us see the definition along with the formulas. It is the ratio between the mass of an atom of element. If single atom is present, this concept is applicable. What about if single atom is not present? So in such cases, it is the ratio between the mass of element in a compound with total mass of the compound. Here total mass of the compound, we can consider this one as a molecular mass. Multiplied by 100. It is called the percentage of the element. Let us see the formula here. Percentage of element is equals to mass of element in the given compound divided by molecular weight of the compound into 100. Let us take an example here. Find the percentage of each element present in CO2 molecule. So this percentage, usually we do the calculations regarding the mass, using the mass. So we can call this one as a mass percentage also. So here, if you take the carbon dioxide is composed of two elements, carbon and oxygen. Each carbon mass is 12 grams. There are two oxygens. 2 into each oxygen mass is 16 grams. The total molecular mass of the carbon dioxide is 44. Then percentage of carbon in the carbon dioxide is equals to mass of the carbon. How much mass of the carbon is present? 12. Divided by total mass of the molecule, that is molecular mass 44 into 100. So you'll get the 27.27%. Similarly, if you want to calculate the mass of the oxygen, here two methods are there. So when two elements are present, so mass of the last element, here it is oxygen, is equals to 100 minus mass of other element. That means mass percentage of the other element. Or else you can do this for this method also. Percentage of the oxygen equals to mass of the oxygen is 32 grams. 2 into 16 means 32 grams. So 32 grams divided by total molecular mass of the compound is 44 into 100. So this is equals to 72.73%. Or else using this formula, 100 minus 27.27% is also equals to 72.73%. So like this we can calculate the percentage of the element in a given compound. Now let us try to see how to calculate the other elements if the element is present not in this type of the compound but in the organic compounds. So there is a calculations for the carbon, hydrogen, different elements are there. Let us see them. And here we are going to discuss only the formulas. Actual procedure of the quantitative analysis shall be discussed in the another video. So let us see the calculation of percentage of the elements of the carbon, hydrogen, chlorine, bromine, iodine, sulfur, phosphorus and nitrogen. So here we have to observe how these compounds are going to convert. So mainly product is important in this case now. So whenever these elements are present in the organic compound, when you treat with the cupric oxide, Cu2O, carbon shall be converted into the carbon dioxide, whereas the hydrogen shall be converted into the water. So in case of the halogens, chlorine, bromine, iodine, we have to use the concentrated HNO3 along with the silver nitrate combination, so that chlorine gives the silver chloride, whereas bromine gives the silver bromide, iodine gives the silver iodide. Here silver chloride is a white precipitate, silver bromide is pale yellow precipitate, and silver iodide is dark yellow precipitate. So in the case of the halogens, when the atomic mass of the halogen increases, automatically the darkness of the color also gradually increases. And sulfur to be identified using the barium chloride solution, which converts the sulfur into the barium sulfate. Barium sulfate is also a white precipitate. So phosphorus to be converted into the using the ammonium molybdate into Mg2P2O7. So here magnesium, phosphorus and oxygen combination is there. Nitrogen we shall discuss separately because its methods are different. The same formulas cannot be applied to the case of the nitrogen. So how to calculate the percentage of these elements when these elements are present in the organic compound. So percentage of element is equals to mass of element in product divided by, we shall write down here, place is not sufficient. So percentage of element is equals to mass of element in product divided by molecular weight of product into weight of product divided by weight of organic compound taken into 100. So this is the formula where we are using to measure the percentage of these elements. So let us see percentage of the carbon. So carbon is converted into the form of the carbon dioxide. How many carbons are there in the carbon dioxide? Only one carbon. So its mass in the product is only 12 grams. Divided by total molecular mass of the carbon dioxide is 44 into weight of CO2 divided, that is after formation, how much mass of the CO2 is formed. That is weight of CO2 formed divided by weight of organic compound into 100. Similarly, percentage of the hydrogen. 2 hydrogen atoms are present in H2O. So that 2 divided by molecular mass is 18 into weight of H2O divided by weight of organic compound formed into 100. Now let us see the chlorine, bromine and iodine. So here you should know that the atomic masses of these elements, so chlorine is 35.5, silver is 108, whereas bromine is 80, iodine is 127, barium is 137, sulfur is 32, whereas magnesium is 24, phosphorus is 31, oxygen is equals to 16. So by using this we have to do that. So let us see the percentage of the chlorine. One chlorine atom is present in the silver chloride. That's why 35.5 divided by AgCl molecular mass, by adding this silver and this value, so we would get the 143.5 into weight of AgCl formed divided by weight of organic compound into 100. Similarly for the chlorine, bromine, percentage of the bromine. Bromine atomic mass is 80 and one bromine atom is present in the product silver bromide. So that it is 80 divided by 188 into weight of AgBr divided by weight of organic compound into 100. Percentage of iodine. So this value is equals to 1 iodine is present here. Atomic mass of iodine is 127 divided by silver 108 plus 127. So this approximately this equals to 235 into weight of AgI divided by weight of organic compound into 100. Now in case of sulfur, percentage of sulfur is equals to 1 sulfur atom is present in the barium sulfate. So that sulfur atomic mass, as I said, 32. Now barium sulfate, barium 137 and sulfur 32. So this is equals to 169. 169 plus how many oxygens? 4 oxygen atoms are there. 4 into 16 means 64. So let us do the calculation. $233. So it is equals to 233 into weight of barium sulfate divided by weight of organic compound into 100. Next, phosphorus. Percentage of the phosphorus. So how many phosphorus atoms are present in the final product of the magnesium phosphate, here metaphosphate? 2 phosphorus atoms are there. 2 into 31. That means 62. 62 divided by total molecular mass. Let us take the help of the calculator to reduce the length of the video. So that magnesium 24 means 48 plus there are 7 oxygens plus 48 and this is 62. 222 into weight of Mg2P2O7 divided by weight of organic compound into 100. So for these elements we are following the similar molecular formula, just by taking the mass of the element present in the product divided by total mass of the molecular mass of the product into weight of the product by weight of the organic compound into 100. in case of nitrogen, this concept little bit shall be different. Nitrogen can be measured using the two methods. One is Dumas method. Second one is Geldahl's method. So in Dumas method, nitrogen is being converted into the nitrogen gas using the again copper oxide. Whereas Geldahl's method, nitrogen is analyzed, it's converted into the ammonia. It is analyzed by using the number of equivalents of sulfuric acid was consumed. So for these two, the formulas are little bit different. Let us see those formulas now. So in case of Dumas method, nitrogen is converted to the nitrogen gas. It is in the gaseous form. So that percentage of nitrogen calculation is equals to total molecular mass of the nitrogen formed here is N2 form, means 28 grams. 28 divided by its volume at STP 22,400 ml into volume of N2 formed at STP divided by weight of organic compound into 100. Now, in case of the Geldahl's method, see, nitrogen is converted into the form of the ammonia, and again it is used in titration against the sulfuric acid so that we take the number of equivalents. That's the reason why here the formula is different from the Dumas method, where 1.4 into normality and volume of the acid consumed. NaVa stands for the normality of the acid and volume of the acid consumed in the titration against the ammonia divided by weight of organic compound. So by using this type of the formulas, we can calculate the percentage of the element present in the given compound. Now let us see the other formats of the empirical formula and molecular formula. You take the screenshot of this. So let's continue this. Next one, molecular formula. So usually molecules are formed by the combination of various type of the atoms. So how many atoms are involved in the formation of a molecule is called as its molecular formula. So the definition of the molecular formula is the actual number of atoms present, the actual number of atoms of various elements. Atoms of various elements present in a molecule is called its molecular formula. So now let us take some examples. Let us take acetic acid. Acetic acid we write down as CH3COOH. This is the molecule. But if you write down its molecular formula, how many number of carbon atoms are present here? 2 carbon atoms, totally 4 hydrogens, 2 oxygens. So writing the various atoms present in the molecule is like this is called the molecular formula. So molecular formula says that exact number of atoms present in the given molecule. Let us take another example. So if you take sulfuric acid direct molecular formula is H2SO4. And if you take the oxalic acid can be represented like this. So its molecular formula can be written as 2 carbon atoms involved and 4 oxygen atoms and 2 hydrogen atoms involved. So that C2H2O4, or else it can be written as H2C2O4, oxalic acid. So writing the exact number of atoms of a molecule is called as its molecular formula. Now let us see the empirical formula. Empirical formula is a little bit different from the molecular formula. Whereas a molecular formula says the exact number of atoms present in the molecule, empirical formula don't say like this. So empirical formula means it is the simplest ratio of atoms of various elements present in a molecule. And here one more line, that is various molecules may have same empirical formula. So by seeing the empirical formula, we cannot exactly say that what type of molecule it is. Let us take an example here. If you take the benzene molecular formula is C6H6. But if you want to convert this molecular formula into empirical formula, you take the ratio. So it goes 1 time each other, so that CH is the empirical formula and this is the molecular formula. Similarly, let us take the acetylene, C2H2. So when you take the simplest ratio of these atoms, then again you will get the CH. So they may have the different molecules may have the same empirical formula. That doesn't mean that they are having the same properties. They have the different properties. Now let us take the oxalic acid. So oxalic acid molecular formula, already we have seen that H2C2O4. But if you write down its empirical formula, it goes simplest ratio as HCO2. Let us take acetic acid. Acetic acid molecular formula is C2H4O2. Then we can write down this one as a CH2O. And if you write down the formaldehyde, so its molecular formula is H2CO, or else we can write down the CH2O, and it is already in the form of the simplest ratio, so that we cannot simplify further. So for formaldehyde, both molecular formula and empirical formulas are same. So this is the empirical formula. So empirical formula do not represent actual number of atoms present in the molecule. It only represents the simplest ratio of the atoms present in the given molecule. Now let us try to see how to calculate this empirical formula and molecular formula and what are the rules associated in calculation of the empirical formula when number of molecules are given, when mass is given, sometimes volume also can be given. Let us see them now. So let us see the rules here now. So first one is starting rules. I am discussing considering that if mass percentages are given, volume and number of atoms or molecules are given, these rules has to be modified later. But starting rules must be only for the when the percentage of the element is given in terms of the mass. So first rule is sum the percentage of all the elements given in a molecule. So whenever percentage of the mass of the elements are given, so first of all we have to sum all the values. Then what happens? If the sum of the percentages is equal to 100%, then there shall be no oxygen present in the molecule, but if the value is not equals to 100%, then the difference value is equal to the percentage of oxygen. So these two rules are very important. Before solving the questions regarding the empirical formula, we must ensure that the total percentages must be equals to 100%. Because in some of the questions, the percentage of the oxygen they don't mention. In such cases, we only have to find out the percentage of the oxygen by doing this one. So ensure that the total percentage is equals to 100. If the total percentage is equals to 100 means there is no oxygen. If total percentage of the masses, whatever the elements are given, if not equals to 100%, for example, total value is equals to 90% only, you got it. Then 10% difference is there. 100 minus 90, 10% difference. So this 10% difference belongs to the oxygen. So oxygen percentages in some of the questions they don't give separately. That we have to do by using this type of the technique. Next one. So once you confirm that the percentages is equals to 100 or else including you calculated the percentage of the oxygen also, then from here onwards we have to follow the common rules. That is, find the number of moles of each element. Then find the number of moles of each element. Means if mass is given, divide by their atomic masses. If a number of atoms are given, divide with Avogadro number. If volume is given, divide with 22.4 liters. And this calculation of the moles of the compounds or elements that we discussed in our previous video, lecture number 12, please do watch that video. Entire theory part regarding the mole concept was available, so that you can understand this particular point and from here onwards remaining concept. Now let us see the next one. Divide the values obtained in the above point number 3 with the smallest number among them. So after calculating the number of moles of each element, then you see among these elements, for example, carbon, hydrogen, oxygen is there. Carbon value you got the 2, hydrogen value you got the 4, oxygen value you got the 8. Then which is the least smallest value? Carbon 2 value. So using that number, again divide all the values with the smallest number among these, so that you will get the moles ratio. So among them, which gives moles ratio. That means simplest ratio of the elements. So in this case, if you get directly the whole numbers, then that is the empirical formula. If the ratio values, whatever you are getting, is not the simple whole numbers, if they are in the form of the fractional values, then we have to multiply again the entire values with a suitable number in order to get the whole number values. So that point I will write down here. So if the values obtained in the above point number 4 are whole numbers, then it is the empirical formula of the compound. So we have to see that it is the simplest whole number ratio. If not, if the values are not the simplest whole number, for example, you got the 1, 1.5, again 1 or 2 is there. So 1.5 is there, that is the not the whole number value, it is a fractional value. So it must be in the whole number values. So that in order to convert everything into the whole number value, we have to multiply all the values with a suitable number. So if not, then multiply all the values with a suitable number to get simple whole numbers. That gives the empirical formula of the compound, and we have to continue till it is formed, whole number ratios. So once you get the empirical formula from this, then the 6th point says that find the empirical formula mass. Find the mass of empirical formula next point says that, so empirical formula is already we are getting the elements, different type of the elements, add all those values, mass of the elements involved in that empirical formula, you will get the empirical formula mass. Then afterwards find the value of n. Here n do not stands for the number of moles, it is simply an integer value. So n is equals to molecular mass divided by empirical formula mass. What happens if molecular mass is given? Directly you can use this formula. If molecular mass is not given, they will give the other information like regarding the vapor density or the density at the STP. Let us see if those values are given, how to calculate the molecular mass. So molecular mass is equals to 2 into vapor density. So double the value of vapor density directly gives the molecular mass. For example, the vapor density of a molecule is 22. Then its molecular mass is equals to 2 into 22. That means 44 is the molecular mass. And sometimes they don't give the vapor density, but they give the volume. That is 22.4 is given. Then you have to take the density of that gas at STP. So 22.4 into density of gas at STP. So using these two, we can calculate the molecular mass. If any of these informations are given, if directly molecular mass is given, we can take that molecular mass. Using that, we can calculate the value of N. And final value is equals to molecular formula is equals to this integer value, whatever N we are getting, that into empirical formula. So that gives the calculation of molecular formula. So using these rules, we have to calculate the both the empirical formula as well as the molecular formula. So let us try to see how to calculate, how to implement these rules by taking some examples. You better take the screenshot of these rules. Okay, let us continue now. So we shall take some examples now. Using this, we can calculate the empirical formula and molecular formula calculations. Yes, let us take an example. First one, question: what is the mass of the question is different. 1 minute. Calculate the molecular formula of a hydrocarbon which contains 85.7% carbon and has molecular mass (84). So let us try to solve this question. Solution. So if you watch the previous for rules, whatever I discussed, the total percentage is not equals to 100%. In this particular case, the difference value is not equals to the percentage of the oxygen. Why? Because the compound is mentioned as a hydrocarbon. That means it contains only hydrogen and carbon. So the carbon value is given, so rest of the value belongs to the only hydrogen, not the oxygen. So here we can see that, let us take the percentage of carbon is equals to 85.7% and percentage of the hydrogen value is equals to 100 minus 85.7%. So this is value is equals to 14.3%. If you imagine the total mass of the molecule is equals to 100 grams, then this value is equals to 85.7 grams and this value is equals to 14.3 grams. So mass of the elements are given indirectly. Using that, let us calculate the total moles ratio. So the first rule is, let us take the carbon and hydrogen. So sum of the percentages is over. Now take the given mass of the element, that is 85.7. Here it is 14.3 grams. Divide with atomic masses 12 and here it is 1. So let me take the help of the calculator. So 85.7 divided by 12, the value is equals to 7.14. So this is equals to 14.3. So now, next one is, so simple values, some values we got it. So using these values, again divide the values with the smallest number. It is 7.14. It is also 7.14. So it gives the 1, it goes approximately 2 times. So carbon, 1 carbon, hydrogen 2. So the ratio of the elements is empirical formula, that is CH2. So here CH2 is given. Let us find out the empirical formula mass. Empirical formula mass is equals to 1 carbon, 2 hydrogens are present in this empirical formula. So that 1 carbon 12 grams and 2 hydrogens 2 grams, total value is equals to 14 grams. Then find out the N value, because the molecular mass is given, that is 84. So 84 divided by 14. So that its value is equals to 6. So N value we got it now. So we can calculate the molecular formula. Molecular formula is equals to N into empirical formula. N value 6. Empirical formula is CH2. So multiply with 6 carbons and 12 hydrogens. So this is the molecular formula of the compound. Let us see the another question. So second question is, an organic compound contains elements percent is given, carbon 30.72, hydrogen 7.70 and sulfur 41.02%. Determine its empirical formula. So this is what given in the question. So our main duty is, first of all, ensure that the value, that given percentage is equals to 100% or not. So rule number 1, sum of the percentages. Is equals to 30.72 plus 7.70 plus 41.02. So this value is equals to 30.72 plus 7.70 plus 41.02, 79.44. Total percentage. Here they did not say anything about the molecule that it is a hydrocarbon. Simply they said that organic compound. That means there is a oxygen as well. So the remaining difference value belongs to the oxygen. So percentage of oxygen. Percentage of oxygen equals to 100 minus 79.44. So this value 20.56. 20.56% belongs to the oxygen. So now total percentage values we got it. Now let us try to write down the elements. Given elements: carbon, hydrogen, next one sulfur is given, and oxygen is also given. So now I am writing like this. You can write down like that also in that format. Okay, let us see, because earlier problem also we solved using this format. Hydrogen, sulfur and oxygen percentages. Carbon percent is given as the 30.72, hydrogen 7.70, sulfur 41.02, oxygen is 20.56. So total percentage equals 100 means indirectly these are given their masses. If you consider the total percentage is equals to 100 grams, then this much grams of the carbon is present. So mass of the elements we are considering now. So now divide these masses with their respect to atomic masses. Carbon 12, hydrogen 1, sulfur 32, oxygen 16. So let us try to see the values what we are going to get here. 30.72 divided by 12, that gives 2.56. This is 7.7. Next one, 41.02 divided by 32. It is 1.28. Next, 20.56 divided by 16. That gives 1.28. So among these the values, smallest values, because now we got the moles values, multiply these moles values with the smallest among these, that gives the moles ratio. So here 1.28 the smallest value, 1.28, 1.28, 1.28 and 1.28. Here anyhow the values is equals to 1. So 2.56 divided by 1.28 gives exactly the value of 2. And now 7.7 divided by 1.28 gives the exactly the value of 6. So we got the moles ratio. That means how many carbon atoms are present? 2 carbon atoms and 6 hydrogen atoms, 1 sulfur atom, 1 oxygen atom is present. This is what the empirical formula of the compound. Like this we can calculate. Let us see the another question. So the question is, on analysis of a compound, it was found that it contains 4.08 grams of sodium, 0.264 moles of oxygen atoms, 5.3 into 10 power 22 atoms of carbon. So determine its empirical formula. So that's why I told you to watch the previous video of the mole concept, because here the elements are given, but all the elements are not in the same format values. Sodium is given in terms of the mass, oxygen is given in terms of the moles, whereas carbon is given in terms of the directly number of atoms. So let us try to calculate their respective mole ratios. So first of all, here you must see that in this case you cannot go through with this particular point, percentage of the elements, because percentages are not given. So we have to consider that only 100% these elements are present in the given compound. So let us see here. So basically sodium is present, oxygen and carbon. Sodium mass is given 4.08 grams, oxygen 0.264, and carbon is given 5.3 into 10 power 22. So let us divide mass with their respective atomic mass 23. Here directly moles are given, moles not necessary to divide. Why? Because our intention is to get the moles ratio. This is the moles only here. So we not necessary to touch this oxygen part. And here divide the given number with Avogadro's number 6.023 into 10 power 23. So let us see the values in this format. 4.08 divided by 23. It is 0.177 moles. This is 0.264 moles, and here this one is 5.3 divided by 6.023 is equals to 0.88. 0.88 into 10 power minus 1. So that value equals to 0.088. So we have to divide all these values with the smallest number among these. This is the smallest value. So divide with the smallest value. 0.088, 0.088, and here also 0.088. So here we get 1, and these values let us try to see. 0.177 divided by 0.088. This value is equals to 2, and 0.264 divided by 0.088. This value is equals to 3. So we got the simplest ratio of the elements present in the given compound. So empirical formula of the compound. How many carbon atoms are there? Let us see the sodium. 2 sodium are present, Na2. 3 oxygens are present, and 1 carbon is present. So this can be written as Na2CO3. Is the empirical formula of the compound according to this. Let us see the another question. So question number 4. An oxide of iron contains 69.94% of iron and 30.06% oxygen. Determine its empirical formula. Empirical formula. So here atomic mass is also provided. Given that iron atomic mass is given as 55.4 85 and oxygen is given as 16. So let us try to sum these percentage values first of all. Solution, sum of percentages. Sum of percentages, that value equals to 69.94 plus 30.06 approximately is equals to 100%. So only this value means only iron and oxygen are present in this particular molecule, and whenever oxygen is separately mentioned, not necessary to go with the first and two steps. Why? Because already oxygen is given. First and two steps helps only to find out the oxygen percentages. And second one, take the iron and oxygen. Iron value is given as 69.94, whereas oxygen is given as 30.06%, their respective masses also. Divide with the respect to atomic masses, 55.85, oxygen is 16. So the values are equals to 69.94 divided by 55.85. This value is equals to 1.25. And here 30.06 divided by 16 is equals to 1.88 approximately. So divide with the smallest value 1.25. Here also 1.25. You will get the 1. And here 1.88 divided by 1.25 is equals to 1.4. So here we did not do the simplest whole number values. So we got the fractional values. So these values are to be converted to the simplest whole number values by multiplying with a suitable number. So let us try to multiply with 2. So you'll get the 2 into 1 is equals to 2. 2 into 1.5 is equals to 3. So that you got the simplest whole number value. So empirical formula of this compound is equals to 2 iron atoms are present, Fe2, and 3 oxygen atoms are present, Fe2O3. So I hope you understand this video. If you have any doubts, please do write to the classroompoint@gmail.com, which is displayed on the screen. Let us meet in the next class. Thank you.